Hello. Today, we will be exploring disease patterns and socioeconomic factors influencing life expectancy. My name is Eric Canihuante, and also I'm working with.
Cameron Hafer, and let's get right into our study here. So, as an introduction here, the purpose of our study is to cover the intricate connections between various health indicators, diseases, and their interplay with some socioeconomic factors, all of which influence the life expectancy of populations across the globe. Um, our data set that we're using to go over this is the life expectancy WHO data set located on Kaggle. Um, It's an exhaustive compilation spanning the year 2000 to 2015, covering 193 countries. It has numerous variables that we'll go over, and a really interesting data set to do an analysis on. The data itself, here's a data set preview of just the first couple of variables. It has the rows, and for each row, it has the country and the year that it was taken. Um, There are 200 or 2,938 entries or rows detailed across 22 columns. These have 20 predictive variables or are quantitative variables, and these are categorized under immunization-related factors, mortality rates, economic indicators, social influences, and a lot of key diseases such as hepatitis B, polio, and diphtheria, um, among other ones. Um, and the initial data kind of preparation or what we're looking at is we just kind of went through and tried to see what the data set is kind of looking like. Um, a lot of different various things that we kind of came across, like some NA values and some brief concepts just to go over. Um, as we go in after looking at the base of the data set and what kind of variables that we had to work with, we decided to start to form our questions. Um, and this kind of outlined the perspective and our focus for the rest of the study. So our first initial question that we came up with is how can we use different diseases to predict other variables, and what models or diseases are most effective at predicting these variables? Um, and this is kind of more self-explanatory. You know, we're using diseases to predict variables like life expectancy and various different health outcomes or GDPs. Um, One example was hepatitis B, measles, and HIV/AIDS might be able to predict life expectancy across different demographics and countries and regions. Um, and For this kind of thing, we focused a lot on regression and clustering as our initial thought process of how we can solve this question here. Um, and we also came up with another question as we wanted to focus not only on just a really narrow perspective, but more on the broad and try to create some results that actually would help people in this industry, in the world that are looking for these kind of results. So we kind of looked at the inverse of the initial question in how can we use non-disease variables to predict diseases themselves. Um, and we knew that this might be a little more difficult, as predicting like GDP with diseases or adult mortality with diseases seems is quite intuitive, but predicting something like polio based off of some other diseases could be quite difficult. But we wanted to see what kind of diseases have some pull, what are most effective. Do we have some models that actually have some results that we could present? So something to just kind of look into there. Um, some examples is looking disease or variables like GDP, schooling, alcohol consumption, um, and same thing. Regression clustering is definitely our main focus for these kind of variables. Uh, just an introduction. So we wanted to do some base models, a little bit of graphing to get a more in-depth look at what our data set looks like. Um, and we found some pretty just basic initial foundings that we wanted to make sure that lines up. Some things that intuitively kind of just sound correct. Um, we found that there's a association between like higher GDP and schooling levels, and these are positively correlated with things like life expectancy rates. And this would be inverse related or correlated with adult mortality rates. A lot of things inverse like life expectancy, everything that kind of looked as if we wanted it to look like. Some initial clustering as well, just to see what this would look like. Some of these graphs also have some pretty interesting visual aspects to it based off of how many different countries it's split into. With 193 countries in a lot of NA values for some of these lesser known countries, we had to do some different or use some different tools to make sure that it visually was sound and that we can actually perform an analysis on this. And that's when we go into how we wanted to approach this as a whole. We found our questions, we found some brief analysis of the data just to see what it looks like. And we found that combining clustering and regression rather than doing them separately allowed us to get some more information and more that we've ever seen with them separately. So that's where we kind of move forward in this data set that you'll see in our actual analysis, our in-depth analysis. And another really important aspect is because of the fact that there's 193 countries and each country can only have up to 16 different values for it, we split all of the countries into one of 6 different regions. A little bit of a code segment below to show how we did this. Just really long code segment to put these into different regions to give us a little more interpretation on these values rather than the countries themselves with a little bit of a low sample count. Go ahead.
So just yes, so just like uh my project partner Cameron was explaining, we did we did use regression and clustering separately, and in doing that, we were able to get like some general like graphs, but we also, as seen earlier, the graphs we saw a lot of outliers and just like a lot of points that when we put them together, cluster and regression, and with the new region variable, we were able to get these kind of graphs that show a lot more. So in explaining what is just going on here, on the left, the elbow method is it's like a way of determining like how many clusters we should really have. Instead of like guessing like how many clusters we should get, through um we analyzed through a certain code segment how many clusters, or an inertia value through how many clusters um, we would have. And the flatter the line, the more clusters you go through, the better. Um, the better the number of inertia would be in determined amount of clusters. So, anyways, we decided like 10 clusters will work as opposed to 4 from previously when we map out just a lot more data. And we have income. We could see income and schooling, 2 factors of socioeconomic factors, and how there appears to be a positive correlation. And then we have adult mortality and GDP, which are like one is both are socioeconomic, but they're more inversely related to each other. So the correlation is not quite the same. And if we go to the next slide, um, we just see even more factors of socioeconomic, like GDP and alcohol and adult mortality, and schooling and adult mortality and clusters and schooling. So, I mean, unlike the first few graphs, there it appears a little harder to see a relationship, but when you factor in the clusters, you could see like where you could actually make out like what's going on. So this is like determining like how important the clusters are for the data and why we needed the elbow method to figure out that we needed so many of them in the first place. And with that, it really helped with the correlation analysis with when using regression models, because like I was describing before, when we had the regression models, but only for like certain variables, but with all the data, um, we weren't able to really get like good like lines of fit. But now, while there are still some R squared values that are very high, negative, and or some mean squared errors that are very high and don't really make sense in the context of the problem for like determining um, GDP, socioeconomic factors, or disease, how they all relate. We definitely do see some clusters where like we get values in like 80, 90%. So we're able to at least have some clusters be good predictors and use a regression from there. So so as an example, some of those good models I was talking about, or would be ones with like high R squared values and low mean squared error values. Um, Life expectancy versus GDP, two factors of, or I mean, life expectancy is the one variable we've been looking at, and in um, relation to in relation to all the socioeconomic and disease factor predicting, and also life expectancy versus GDP, um, and um, life expectancy versus GDP per capita. So yeah, it's yeah, you could clearly see a trend, even if there are some outliers, especially in the top right graph. There's still a trend that's visible, and through high R squared and low mean squared error values. And again, some good models like we described earlier, we can see positive correlations through regression models, or yeah, through the regression outputs. And that leads us to the bad models. What makes a bad model a bad model? It's it's just at this point when there's like a few outliers that are like very, very far out from the rest of the data, like on the graph on the left, uh, again with GDP and life expectancy, or on the bottom right where we have a we have points above and below the line on all sorts of different GDP per capita values or life expectancy values. Yeah, those kind of graphs gave us the low R squared and high mean squared error values. And again, some more graphs just to illustrate this point as well. And just as a quick recap, um, what if, what insights and implications did we get? So we noticed some clear patterns showing how money, education, where you live, um, can change life expectancy or how long you live. I guess some things to think about, like having a stronger economy and better schools would mean people live longer. Sounds intuitive, but through running this data, we were able to see that. Um, uh, and now what kind of action can we take from this? So we were able to see the socioeconomic factors and determine positive correlations, but also we were able to see how um, factors could negatively affect life expectancy, um, like diseases, and using diseases to predict life expectancy. So um, if we take both those positives and negatives, like prevention, but also like invest in, then we can encourage more spending on schools and growth, and also like factors to prevent diseases like immunization, even if we didn't look at that directly. So yeah, I think that about sums up all our data, which was a lot.
Yeah, and just wrapping it up, some of our results, we initially kind of wanted to look at a lot of disease factors to predict variables, but a lot of our socioeconomic factors kind of had a lot more pull. And so we decided to use a lot more of those and shift our kind of our study. And we found a lot of things, but that were, more intuitive, but to see predictors like GDP having a high pull for some of these things like life expectancy, maybe was a little bit more than we expected, and got some good results using that. And that kind of wraps up our presentation. Thank you for watching. I'm Cameron Hafer.
Thank you, and I'm Eric Canihuante.